Okay, looks like it's time to start. Welcome to Lecture 2, and thanks for coming back. So this is what we're going to do today. I'm going to talk about more about design metrics. We talked about design metrics, performance, cost, and power last time. We'll get into a little more detail about that. And then I'm going to review some basic logic, digital logic concepts. You may have seen this before, but I think it's a good review. We'll talk about design implementation alternatives. You'll see what I mean by that in a few minutes. And associated design flows and a little more detail about ASIC design. Okay? So before we do that, just to remind you from last time, Lecture 1, what I think the important points are. One was that we talked about Moore's Law, and you should understand now that Moore's Law is slowing down. We're continuing to make advances with processing, but it's coming at a slower pace than it was before. Okay. So in order to continuously improve the performance of our computing devices, we have to be a little more clever than we were in the past. We can't just wait for technology to give us that boost. Okay. We talked about Dennard scaling, which is the kind of scaling that we do in order to keep power consumption under control. And this is sort of ended a decade ago, so most designs now are power limited, so we do pay particular attention to power consumption when we do designs. We talked briefly about multi-core specialization and customization. This is a way to provide more performance without incurring more power consumption. Okay? It's a more energy efficient way to do it. We'll talk more about this later in the semester too. Talked about the fact that design costs are high now, right? Because there's so many transistors and so much complexity to the chips and other devices that we design. Right? So we need to have methodologies and tools that can help us manage all that complexity. And that's some of what we're going to be talking about today. And we talked about the fact that there's trade-offs between performance, cost, and power in all kinds of designs. Okay. And this is a topic that we will visit many times throughout the semester. It's kind of an underlying theme of this course, because learning how to do good design is learning how to manage those trade-offs. Right? And we talked about this concept of Pareto optimality. It defines the best designs, the designs that have the best trade-off between these parameters. Okay, so any questions on last time before I get going on the new stuff? Okay, so let's talk about implementing digital systems. So this is something that I presented last time. The first bullet says, given a functional description and performance, cost, and power constraints, come up with an implementation using a set of primitives. That's what I define as being the design process. That's what we have to do. So you're giving a functional specification, like you want to build a widget that does some function. Maybe it's implementing an instruction set, like you're building a processor. Maybe it's executing a neural net, all right, for instance. That will give you the functional description. And then you'll get some constraints on the cost, performance, and cost. And you have to figure out how to put those primitives together in a way to implement that function. All right. When we do that, these digital systems are going to have some inputs, some outputs. What's inside here in a digital design is really composed of just combinational logic and state elements. Okay. And we'll talk about both of those kinds of things. They're both, each one's a class of circuits. Right? And you've probably seen both of these before. You've seen state elements in the form of flip-flops or registers or memory, and you've seen combinational logic in the form of logic gates put together in order to implement some function. Okay, if you haven't seen that yet, you're going to see it here. All right. So it's very simple. That's really the whole story. If we learn about combinational logic and we learn about state elements, we can design any digital system. All right. So we're going to talk about a methodology that we use to arrive at some solution given the functional description and given the constraints. So this is kind of the standard way we do it these days. And it's a kind of a stack. And we move from the top down through the bottom. So at the top, we get some specification. This is a description of what you'd like your design to do, right? You'll see this firsthand if you're taking the labs. At some point in the semester, we will hand out to you a project specification. This is a specification of the functionality that we'd like your project to be able to do. If you're working for the company, it'd be the same way. Somebody will come up with a functional description for what this device needs to do in order to fit into the product that you're building, right? That's usually, oftentimes it's in plain text. It's just a description, okay? We turn that into a more specific and a more executable specification by oftentimes modeling it. Quite common to use C or C++. So you write a program that has the same functionality that you'd like the hardware to have, right? It's going to run much slower than the hardware, but it will be functionally correct. This gives you a way to test it, to test your specification and make sure that it really is what you want it to be. That if you apply some input, you get the proper output, right? What we say by that is you're validating the model. You're validating that what you want to build is really what you think you want to build is really what you're going to build, right? It tests all the different combinations of inputs and what the output will be in that case, right? So you validate the model. Once you have that model, we usually then devise what we call a microarchitecture. It's a way to put together blocks in order to implement that function. Okay. You've seen this maybe in 61C where we talk about the microarchitecture for the RISC-V, where we put together ALUs and a register file and maybe a multiplexers and memory interfaces and those things. That kind of block diagram level description of the structure of the hardware is what the microarchitecture is, right? Once you have that, then we take that description and we break it down into logic description with often for us it'll be in Verilog. So we'll write Verilog that describes this microarchitecture, right? And then we're going to test this. We'll test this to make sure that it's working correctly. In fact, what often is the case, we'll compare this logic description to the C++ model and make sure for a given input they produce the same output, or for a given string of inputs it produces the same output, right? But then, given the Verilog, which is the hardware description language, it describes all the logic gates and flip-flops and how they're all connected together. Then we use tools that turn it into a physical design. Okay. If we're building an ASIC, we'll actually build the layout. If we're using an FPGA to implement the design, then we generate the proper files needed in order to program the FPGA. Right? But it's the physical level design. It's the physical realization of that logic. And then if it's an ASIC, if it's an FPGA, we already have the working part in hand. If it's an ASIC, we can send it out for manufacturing. And then a few weeks later or a few months later, whenever it is, the chip will come back and we can test that. And then we do some tests down here to make sure that what we build actually works. So the process of testing out these various models. So what you see here is a high-level model. And we work our way down, all the way down to a physical realization. And the key to this methodology is that at each level, we preserve the same functionality as the level above. At least the essential functionality, the functions that we care about, right? But we add more details as we go. And as we work our way down from the top to the bottom, we can guarantee that everything still works, because we can check each layer above against the one above it. So if you know the plain text description is right, then you could test out your C++ model and make sure it matches the textual description. And then, like I said, once you have the Verilog model, you can simulate that. And once you have the gate level model, you can simulate that and check it against the model above. So at each point, we can determine whether or not we're introducing bugs or mistakes. Right? So you have something working on the top, and we push it all the way down, and we have something working at the bottom. And just so you know, we make this distinction between validation and verification. When we do verification, it's at the upper levels. And there we're asking the question, have we built the right thing? Does it have the right specification? At verification, we're asking a question, have we built the thing correctly? Have we implemented it in such a way that it has the correct function, the function that we care about? All right, so I just wanted to show you an example. Last time I said that the kind of state-of-the-art process is 7 nanometer CMOS. This is kind of one of the latest chips. This is the Apple A12, which goes into the new Apple cell phones. I don't remember which ones. iPhone 11 maybe. You can see in here that there's this kind of hierarchical design. Here's the whole chip, but we can break, at least we can see the top level of the hierarchy where you have these various blocks. Here's a neural engine. This is for doing neural network inference. There's a bunch of processor cores. There's cache. Here's a GPU for doing the graphics and the display. There's some interfaces off to external memory, DRAM memory. There's a big area in here. I don't know what it is. If anybody can figure that out, let me know. I thought maybe it was memory, but it doesn't look like memory. I thought maybe it was just big cache, like level 3 cache, but it doesn't look like. The memory blocks, you can see they're very regular looking, as we will see later in the semester. This is kind of irregular looking, so I don't know what's up there. Okay. This is, it's kind of washed out, but this is the board that's inside the cell phone, and here's the big chip sitting there. Right, it's a pretty big chip. So we call this SoC, system on chip. It's more than just a processor. It's got a bunch of different things combined together on one chip. That's what we call it, a system on chip, SoC. All right, so now we're going to talk a little bit about design metrics again. Last time I introduced this idea about the trade-offs between performance, cost, and power. And we talked about Pareto optimality. And the fact that these design trade-offs exist everywhere in the design process, at every block and every level in the hierarchy, we have trade-offs to be made. All right. I want to talk a little more about what we mean when we say performance, and what we mean when we say cost, and what we mean when we say power in this domain, in the domain of electronic design. So first, performance. So as you may know, there's actually 2 different measures for performance depending on what's important to you. We have throughput and we have latency. Right? And what throughput is the number of tasks performed per unit of time. It could be operations per second, for instance, where a task is a simple operation. It could be that a task is a more complicated thing, like a whole program, right? But the measure is the same. It's the amount of work you can get done per unit time. Here's an example. This is the Google TPU. TPU is people know what TPU is? Yeah, it's their tensor processor unit. This is a special processor they built for doing neural network inference and maybe training. I don't remember. But it's their attempt to make special hardware to accelerate machine learning. They call it TPU because they invented this TensorFlow language way of defining neural nets. They put 4 of their processors together on a board, as shown here, and then they plug a bunch of these boards into a rack, and they put these in the server racks along with their general purpose computers, and so they can accelerate certain operations that happen up in the cloud, operations that use neural net inference. They define their performance as teraflops, T-flops, teraflops, so billions of floating point operations per second. For them, a floating point operation is a 16-bit floating point, because for neural nets, you may know that you don't need very high precision. You can get by with only 16 bits. So they've invented this thing they call bfloat, which is bfloat 16, which is 16-bit wide. Okay. And their board can do 420 billion teraflop operations per second. Right. So that's one way they measure the performance. Right. You have to watch out when people give you performance numbers in ops, because ops could mean different things to different people. It could be integer operations. It could be double precision floating point, like the people that do scientific computing. They use 64-bit floating point numbers. Right? So to really understand the performance, you have to understand what the definition of op is as well. Right. And you also have to watch out for peak versus average. So this is a peak number. On any one application, it probably doesn't get very close to that. You know. A well-designed computer might get, I don't know, 80% peak, because there's other things that would be if all the ALUs are working all the time, but sometimes there's stalls due to dependencies, or there's stalls due to memory problems or other things, right? So this is kind of a peak number is like we call a speed of light number. It's the number that's guaranteed not to be exceeded, right? Any real application will be a little lower, right? So you have to watch out. That's the difference. So average throughput on some set of benchmarks is probably a more realistic measurement of performance. Okay, that's throughput. Latency is the other one. That is other performance measure, and that says how long does it take a task from start to finish, right? These two are not necessarily simply related because of overlapping and pipelining, as you learned, and we will talk more about it this semester. So you may be doing more than one task at a time. For instance, facial recognition on a phone takes tens of milliseconds. So to recognize one face might take 20 milliseconds. That would be the latency of that operation, right? Sometimes it's expressed in terms of clock cycles instead of real time, which is fine, but then you have to know how long a clock cycle is to really understand what the real latency is. Okay. You also, again, have to watch out between average and worst case in here. You might be, the performance of your system might be determined by the worst case, and there may be a small number of cases that take a long time that have longer latency than others. Okay, so that's performance. Energy is another one of our parameters we care about. Energy and power, again, they're related, and sometimes we care about one and sometimes we care about the other one. So energy is in joules for us. Energy tells us we need a certain amount of energy to perform a task. How little or how much energy it uses tells us the energy efficiency. So we could talk about joules per operation, for instance. It's a sad fact of doing computation. The electronics that we build use energy in order to do what they do. Right? They take energy, they turn it into heat, primarily, and some useful result, hopefully. So for instance, we could ask how many joules does it take to add two numbers or to fetch an operand out of memory? Right? It'd be a really tiny number in terms of joules. A joules is a joule of energy is a pretty large amount of energy. Batteries store energy, right? They store a certain amount of energy. So every time you do a computation, it drains your battery a little bit, right? The battery usually the energy in a battery could be expressed in joules, could be expressed in watt hours, right? Could be expressed in something else. But in the end, it really has to be some measurement that's equivalent to energy, like joules. This is also what PG&E, Pacific Gas and Electric, the electric company, in California it's the electric and gas company, when they charge us per unit of energy. Right? They charge in terms of kilowatt hours. How many joules in a kilowatt hour? Anybody know? A watt is 1 joule per second. All right. So somebody should be able to compute that. I don't remember what it is. If we know a watt is a joule per second, watt hour, so we just need, how many? 3.6 million joules in a kilowatt hour? Oh,
like
okay.
Hour is 60 minutes, 60
okay.
seconds per minute, 1,000.
All right, that makes sense. So it's a lot of energy, yeah. And I think I pay 20 cents per kilowatt hour, something like that. Okay, so that's energy. Power is really, as you know, it's energy per unit time. It's at the rate at which we use energy, right? Energy is dissipated per unit time. We usually talk about it in terms of watts. It's really joules per second. The reason this is important to us as designers, so energy is important to us because we pay for energy from the power company, And we have batteries that have a limited amount of energy in them. So you want to have energy efficient circuits so that your batteries last a long time, right? Power is important to us because the amount of power that we're burning really dictates how hot the device gets. The amount of energy per unit time that the circuit uses determines how warm the device gets. And if it's going to be in your pocket, it's really uncomfortable if it's more than a couple watts, like 5 watts, I think, is the limit. Right? So that's important. It sets the cooling requirements. That's because these devices don't have any heat sinks or fans in them. It would be really awkward to have a fan in here. These desktop machines, if you notice, if you're streaming and doing a lot of stuff, the fan will come on. That's to cool down the CPU. It would be annoying to have a fan in your cell phone. So it's passive cooling, we say. It's just, in fact, it's all covered up, so it's not a very good opportunity to get the heat radiated off. There's not good heat sinks here. So it's limited to a couple watts. So that's one thing. Also, if you're running a data center where you have to have active cooling, for instance here, this thing, it uses so much power. The reason you know it uses so much power, you look at these power wires, are really these big fat wires bringing the current into these things. To run them fast and to expend a lot of power, they have to cool it with liquid. There's liquid cooling, so there's plumbing that hooks up to these boards, and they circulate cold water by the chips to pull the heat away. It turns out water is a much better conductor of heat than air is, so an effective way to cool electronics is to use water to pull the heat away and then radiate it somewhere out into the environment. And it's been done from time to time on various computer systems and servers. And you know the people that do the hot clocking and play games at extremely high speed on their, what do you call those kind of machines? Those computers that are desktop, or what do you call those? Tower computers, I don't know what you call them. They use liquid cooling so that they can run the CPUs at a higher rate and expend more power. Okay, so that's the other reason for power is if you have to pay for the cooling, the air conditioning, if you're running a data center. Right? This is why it's more cost effective to put the data centers up north, like up in Seattle and places where it's cooler, because it's easier to get rid of the heat by putting it into the environment than it is if you're in a warm climate. All right, so that's energy and power. We'll go into more of these later in the semester when we see exactly what it is about design that has an influence on power and energy. For now, though, I just want to make sure you understood what we mean when we talk about energy and power. And the last one is cost. And cost is always also an interesting story. There's 2 types of costs. There's non-recurring engineering costs and there's recurring costs. The non-recurring engineering costs, these are the costs that are the cost to develop a product. It's not the cost to build it, it's the cost to do the design. In practice, what this means is if you're at a company and you're designing a chip, you have to pay a bunch of engineers, you have to buy the CAD tools, you have to pay the engineers' salary and benefits. And this is over some period of time, however long it takes to do the design. And that's a fixed one-time cost, right, for each chip or each product. Somehow this gets amortized. That cost then, it gets spread over the cost of, it adds an increment to the cost of each unit that you build and ship, right? So for instance, if it takes $20 million, which is maybe what it would take to design a chip in a company these days, and you're going to produce 100 million units, this would add 20 cents to the cost of each unit. That's what we mean when we say it gets amortized over all the units shipped. So that's one kind of cost. The other type of cost is recurring costs. And this is the cost to manufacture, test, and package a unit or a chip or whatever it is that we're designing. Right? So these days, and I'll go into more detail on this in a minute, but process wafer costs are around $10,000 for a whole wafer full of chips. Right? So we do the design, we send it out for manufacturing, we get some number of wafers back. We have to pay something like $10,000 or so per wafer. And on that wafer, we get some number of chips, and they get cut off and put into packages. If it's on this particular process node, on a wafer, we could get maybe 50 to 100 large FPGA chips or GPU chips, right? Or maybe 200 laptop CPUs or cell phone SoCs. Maybe they're made small so that they're cheap. Maybe we get 1,000 of those. So let me go into more detail about the costs associated with ICs. So the real cost per IC is this cost, which is the variable cost. The recurring cost, so now the variable is another word for recurring. It's the variable cost per IC plus the fixed cost divided by the volume. So this is the amortization of the NRE. Right? So there's a little increment on each one to amortize that NRE. Right? So how do we get this cost, the IC cost, the recurring cost? Well, the variable cost here is the cost of the die plus extra stuff. It's the cost of the die test. Is we have to pay to have it tested or buy the equipment to have it tested or something. There's some cost associated with testing the die. And the cost of the packaging, we have to put the die into a package, and that costs something. Buying the package and the process of putting it in. And then divide by the final test yield. So if we go through this process, we fabricate a bunch of die, we put them in a package, we test them, and only half of them work, guess what? The cost of every package die just doubled, right? That's this denominator here. So if we have 100% yield, if they all work, this is a 1. If only 10% work, then they've all gone up in cost by a factor of 10, right? So the yield has a direct. And by yield, if you don't know that word, that means yield says how many of what percentage are good versus what percentage are bad. Yes?
Could you define exactly what a die is?
Oh, a die is, yeah, here. So when this is our design. It's replicated many times on the wafer. Our design gets cut out and put into a package. That little piece we cut out is called a die. I forgot where the word comes from, but it's really just, these are electrically isolated from one another. They're just all fabricated next to one another for convenience. And then we slice it. There's a saw that comes and cuts them all up into individual. So the little individual piece of silicon is called a die.
Okay, dumb question, but why is the wafer circular then if you can't like cut out a square die?
Yeah, it would be more efficient if it were rectangular, wouldn't it? It's the way the crystal. This is, we fabricate the circuits on single crystal silicon, or as close to single crystal as we could get to avoid any impurities. It's just the way the electronics work. We need crystalline silicon. They're grown from a seed and then pulled out of molten silicon. And when you pull them out, they just naturally form a cylinder. And then it's sliced up. So it's the way, if you want to grow, it's the way the crystal grows. We grow a big giant crystal of silicon and then slice it up. The crystal happens to be round. And just throw away the ones on the, so there's some partial die here around the perimeter. Those just get thrown out and they just contribute to the waste. All right, so here we are again. Cost, I think, oh yeah, okay. So the cost of the die is going to be the cost of the wafer, whatever we pay for that, divided by the dies per wafer times the die yield, right? We divide the cost of the wafer by how many dies there are in that wafer times the die yield. All right, so just pushing this along. So the yield, what's the yield? The yield is the number of good die per wafer divided by the total number of chips per wafer, right? Times 100, because it's a percentage, right? So if we want to get the die cost, the wafer cost we know, let's say it's $10,000, something like that. The die per wafer we can figure out in a minute. And the die yield, I'll tell you how to get that in a minute too. Okay, so here's the die per wafer. Wafers are round. We cut it up into pieces. We can use the diameter. We know the area of the wafer. We can use pi r squared here, right? Assuming it's square, divide by the die area. That gives us the total number of die here. And then we have to subtract off these ones on the perimeter that are partial die. That's given by this formula here. Right? So if we use this, we get the total number of die per wafer. If we know the cost of the wafer, we need to know what the yield is. The yield has to do with defects. Okay. Some of the die will not work, right, because there will be some kind of defect. The defects come up because of the manufacturing process. There may be some impurities in the materials that are being used, the air or the water, or in the crystal and silicon itself, or in something else that we deposit. Right? All these kind of faults that could happen, they're all kind of modeled as defects. And they just pop up randomly. Right? If a defect pops up on a chip, chances are that chip's going to be no good. Right? And we'll figure this out with the final test. And some of them will test as being bad, and we throw them out, and then that will decrease our yield. So for instance, here's a yield of 25.25, 25%. Of these 4 giant die here, only one of them is good. So that's a yield of 25. On the right, we have a yield of 0.76. You can see here. So it's kind of a, just the bigger, and obviously the bigger the die, the higher the probability that there will be a defect there. If the defects are uniformly and randomly distributed, which we'll make that assumption for now, and we're making a bigger and bigger die, as the die gets bigger, there's a higher probability that a defect will lie within that die, and the die will not be any good. That design will not be any good. Right. So here's it's kind of a standard formula that we use for computing die. It's defects per unit area times die area divided by this empirical parameter alpha to the minus alpha. Alpha is approximately 3. Right. So if you work all this out, it turns out the die cost then is some function of the die area to the 4th power. Okay. It's a very strong function of area. Okay. So the bigger die are going to cost more because they will have lower yield. The probability of being able to, if we built a really big design that took the whole wafer, there would be almost no chance of getting that to be perfect because its chances of hitting some defect would be so high. Right? So there's, as a designer of ICs, there's always a push to make the area as small as possible for one reason, to increase the yield, which is going to lower the cost because the yield directly impacts the cost. And as I said, there's big benefits by making it just a little bit smaller because it's to the 4th power. So when we talk about cost, usually we mean die area, die cost, which is directly proportional to die area. Right? Okay. Any questions on that? I'm going to kind of move on to away from metrics onto doing kind of a simple review of digital logic concepts. Okay. Here's my hand-drawn logic gates. This should be a review if you've taken 61C. If not, you've seen logic gates in some other class. Seems to be a really popular thing to talk about. They're not the most important part of digital design, but it's the thing that everybody talks about because Boolean algebra is fun. And but we should understand, and we will use logic gates. They're still important to understand. But these days, we don't really design much with logic gates. We design with a hardware description language. And the tools automatically infer the proper logic gate structure for us. But it's good to know what's happening underneath. Right? So here's our kind of favorite 2-input logic gates and or not 1 input. NAND, NOR, XOR. Here's our little truth tables here, which is the definition of the function of the logic gate, right? You put a 0, 0, and you get a 0, for instance, in the AND. Okay. So these are the primitive elements out of which combinational logic circuits are constructed. I said all digital designs are made up of two things. There's state elements and there's combinational logic. The combinational logic part can always be described as a set of logic gates in some connection. Right? That's why we like them. In some technologies, there's a one-to-one correspondence between logic gate representations and the actual circuits. Okay. So when we design an ASIC that has a standard library of primitive logic gates, your circuit, what's residing on the chip is actually a collection of logic gates that are wired together. Right. And we'll see more of that in a few minutes. If other times, they're just an abstraction that we use on our way. Remember, I talked about those different layers of abstraction that we use to go from a high-level specification to an implementation. Sometimes logic gates are just a level of abstraction that we use, and then we implement that functionality through some other means. And that's what we'll see in field programmable gate arrays and FPGAs. There's no real logic gates in there. They just have a way to pretend or act like there's logic gates in there. Okay, so that's the basic set. A couple questions. Do we really need all these different types of logic gates? And everybody should know by now, you don't. In fact, there's been computers, the Cray supercomputer, the first supercomputer, or one of the first supercomputers that was built out entirely of NAND gates, two-input NAND gates. You can actually even build state elements out of logic gates, out of NAND gates and NOR gates. So you could, if you're on a desert island with nothing but a pile of NAND gates, you could build a computer if you wanted to. You wouldn't have a keyboard or a screen, but you could execute in programs. So it's a powerful concept. That's why we like it. And so you need, what do you need? You need and, or, and not, right? And you can get and, or, and not from just an and if you want. You can turn an and into actually all you need is and not. Is that right? Yeah. Or nor and, or and not. So you can turn this into an inverter and into an or an and you can do the same thing with that. So you have a lot of choices here, but for efficiency reasons, we usually keep all of these in the library because it's not always the most efficient thing to do everything with just one type of gate. And we'll talk much more about these and what they look like at the transistor level later in the semester. The other thing is, how about gates with more than two inputs? Of course, we can extend this, and there's gates with more. Here's a 3-input NAND. Some people call it a NAND 3. And you can extend, kind of extrapolate from the truth table, or the definition of the gate, to extend it to more inputs. In this case, this output of this NAND gate is a 0 if and only if all the inputs are a 1. Just like for the 2-input NAND, the output was a 0 if and only if both inputs are a 1. And then there's more complicated composite gates that might combine things. Here's a thing we call a and or invert. It ands two things together and then ors something else in and then inverts the output. Right? And the reason we might want to have these are fairly efficient to implement at the transistor level. And they might give us this combined gate is implemented in a way that's different. It's not just an AND gate. Functionally, it's an AND gate followed by a NOR gate. But at transistor level, it would actually be more efficient. We can do this with fewer transistors than we would have if we had an AND gate followed by a NOR gate. Okay. And that's why they exist in the library. They provide a more compact way to get certain functions that may be popular. In CMOS, we usually don't have gates that have more than 3 or 4 inputs. Because as we will see, as you start putting more inputs together, transistors get long strings of transistors in parallel, and that slows everything down. So gates with too many inputs are slow. So we might be better off cascading gates rather than having gates with a large number of inputs. Now, the interesting thing about logic gates is they're a very powerful abstraction. I said sometimes they're also an implementation, but as an abstraction, they're really interesting because there's many different ways to build logic gates. They have been built out of many different technologies. Here's the CMOS gate, and we'll talk more about that because CMOS there's by far more CMOS transistors in the world than any other type of transistor. Right? It's because they're very cheap. Because of Moore's law, we've gotten to the point where they're very cheap and easy to build, and it's a popular technology because we can scale down so much. There's other technologies, other ways to build logic circuits and logic gates. This is an old one, DTL, diode transistor logic. That I think is I don't even know if that's an AND gate. I think it's an AND gate. You can do logic gates with hydraulic systems, right? Here's this certain valve that implements an XOR and another one that implements an AND. Right? People have done mechanical gates out of Lego. There's Lego logic gates, right? What this means is if you have one of these gates and you have it in an inversion, you have an inverter and one of these gates, you can build a computer or build any other digital system out of those if you want. You could build, your x86 processor out of Lego gates. It would probably fill up more than this whole room. It would fill up the whole floor, but it would work in principle. It might be really slow, but it would work. And you could guarantee that it would work. That's the neat thing about logic gates. But we'll stick with CMOS in this class. But by the time you're in grad school or graduated, there might be some new technology that implements logic in some other way than CMOS. So that's why we think when we teach you about logic design, teach you about digital design, and we keep it fairly abstract, that's knowledge that will be useful even if you're using quantum spin logic gates, right, versus CMOS gates or whatever they are when you're having your career later on. Now, I said there's lots of different logic gate implementations, but they all have a property in common, right? In order to be a workable logic family or logic gate, you need to have this property of restoration or regeneration. And what this means is the second bullet here. The circuits need to ignore noise and other non-idealities at their inputs and generate cleaned up signals at their output. You don't want to pass the noise through, and worse yet, you don't want a circuit that amplifies the noise and makes it worse. Because if you cascade a bunch of these gates together and if there's a noisy signal going into one, you'll get a noisy signal coming out of that combined with more noisy signals, and you get more noise, and pretty soon you don't know if it's a 0 or a 1. You don't know what the signal is anymore. It's just a bunch of noise. So the only way to make a feasible and working logic family is that at each stage we take this non-ideal looking signal and we clean it up and make it look very ideal. Right? And that's the process of restoration. And I can show you in simple form how CMOS gates and other logic gates do this. And I'll demonstrate this by looking at a one input gate. One input gate is the inverter in this case. The transfer, we call this the voltage transfer characteristic. It's a curve that shows the relationship between the input voltage and the output voltage. Right? This is VDD. This is the maximum voltage in our system. For the technology we're using in the lab, 7 nanometer process, it's about 0.7 volts. For many years, it was around 1 volt. When I was in school, it was 5 volts. But it's a couple volts usually. Okay. And this is the maximum voltage. That's what we use to represent logic 1. And then 0 volts we use to represent logic 0. Right? So an inverter, if you look at the output response to every voltage we could put at its input, it makes a curve like this. Okay, this is ideal. Right? So input is low. Let's say we ramp up the input voltage here. The output stays high. At some point, it changes, and we get to this point, and then all of a sudden it starts interpreting this voltage as a high voltage, and the output will be low. Right? Remember, inverter just switches from 1 to 0, 0 to 1. This fact that it has this really high slope right here is what makes it restoring. So here's a funny graph. So if this is my ideal, time is running this way in this picture. So here's a waveform showing some voltage that we're going to put into the inverter. Put it into this, map it through this function here, and it will come out like this, nice and clean, right? Because all this squiggly stuff gets interpreted as in this regime and just gets put out as a high voltage. All this stuff above this threshold point here gets interpreted over here and gets put out as a 0, and then we go back. Right. So you can see if we push this noisy signal through the characteristic of the inverter, what we get out is a nice, clean, ideal-looking signal. Of course, on the way then, this one will hook to another circuit, and then in the way, on the process of getting over there, they'll add a little noise, but we got rid of all the noise at this point. So we kind of decouple each stage. Looked at this for an inverter. Every logic gate in a CMOS family has the same type of characteristic. Right. Now, that's ideal. We can't really build anything that looks like this, but we can build this. If we put together in the way that we'll be talking about, put together our transistors, PMOS transistor and NMOS transistor for real inverters, and we measure it, this is kind of what we get. Okay. It's not infinite gain at this point. It's got finite gain, but it's pretty steep. All right. So if you think about it, what's important here? What is important is that this inverter is acting like a nonlinear amplifier. Right? If you're taking an analog class, you work really hard to make your amplifiers linear. But here it's kind of nonlinear. It's got this really steep discontinuity. It's got this kind of discontinuous behavior here. It would make a really lousy amplifier. It'd introduce all kinds of distortion, right? But it serves our purpose here because this nonlinearity is the essential thing that we need in order to have restoration. In a more philosophical sense, it's this nonlinearity that forces a decision. The gate is forced to call the input a 1 or a 0. It can't say, oh, I got some value at my input that's halfway between 1 and 0, therefore I'm going to put something at my output that's halfway between 1 and 0. It doesn't, the circuit doesn't allow that to happen. It forces a decision, right or wrong, that the output's either going to be 0 or 1. It's an important thing. If you study neural nets, by the way, neural nets have nonlinear elements as part of the inference process. If you don't know what I'm talking about, don't worry about it. But that nonlinearity is an essential part of the neural net being able to do classification or make decisions. Right? So it's a fairly deep concept, and we see it here in logic gates. Okay, so that's restoration. And something about inverter voltage characteristic. Yep.
Did you choose an inverter because it's common in like a NAND gate? Like why not use just like an identity gate?
If you looked at the voltage, if you look at the voltage transfer characteristic from an input of a NAND gate to its output, it'll have a similar thing. It just moves. It may move over a little bit. The reason I use an inverter just because single input, it's easier to see what's going on. We don't have to worry about what the other input is doing. But they all have a similar property to this. And it doesn't matter that it's inverting or not. Same thing, even if it's a non-inverting gate. But we can't really build non-inverting gates in CMOS, as we'll see later. Okay, so that's logic gates and restoration. So we use logic gates, as I said, to implement combinational logic blocks. So let me talk about combinational logic. Here's an example. Here's a 4-input Boolean function. So combinational logic for us means Boolean function. It's a combinational logic block is an implementation of a Boolean function. A Boolean function is a function of variables that take on one of two values, either 0 or 1. Okay. The reason we do that in digital designs is that it's very easy to make circuits that can represent zeros and ones. Anything other than zeros and ones is hard and full of noise and not very reliable. So we just stick with zeros and ones. Okay, so we don't know what this function is. It could be anything. That's why I have here, I filled in the truth table here. What the truth table is, it tells us what the output value will be for each input combination. So here's all the input combinations. And I don't know what the output is. You could fill it in yourself depending on what you want f to be. Okay? This is just the generic form. The important thing about combinational logic blocks is that the output is a function only of the current input. There's no history in here. It doesn't know what it had at its inputs before. It responds only to what it's at its inputs. In a mathematical sense, this is more like a pure function. Or in a programming language, it's a pure function. No state, no side effects. We can represent this with a truth table. Right? The output is explicitly specified for in each input combination. In general, combinational logic blocks may have more than one output, in which case we'll just add more columns to the truth table, one column for each output. All right. Here's an example. Here's a 2-input adder. This one, 2-bit 2-input adder. It adds two 2-bit binary numbers together. These 2-bit binary numbers we can use to represent integers 0, 1, 2, or 3. Right? 2 bits, 4 different numbers we can represent. So what I did here is made the truth table for this. I enumerate. Here's adding 0 to 0. Here's adding 1 to 0. Here's adding 2 to 2. Right? Should be 4. It is. Right? The output's going to be at least 3. You know, if you add 2 n-bit numbers, you get n plus 1 bit at the result at the output. This is all unsigned right now. We'll talk about signed numbers later. And so here it is. This is the full definition of this function. Now, what's inside the block, we don't know necessarily right now, but we're just defining it abstractly. We could do the same thing for a 32-bit adder, right? If we wanted to. We'd have 32 bits here and 32 bits here. In order to enumerate all those possible input combinations, we'd have to have 2 to the 64 different rows in our truth table. 2 to the 64 is a pretty big number. We couldn't put it on one slide, or I couldn't put it on, I don't know, somebody could, what's 2 to the 64? It's a big number. Right. But in principle, it still works. We could still uniquely define the function of that 64-bit integer adder with a truth table if we wanted to. We'll return to truth tables later on when we talk more about implementing circuits. I wanted to introduce it now because it's a unique definition for the function of the logic block. The nice thing is, and the reason we're going to return to it later, is any combinational logic function that can, meaning a function that we can describe as a truth table, can be implemented as a network of logic gates. So if we can figure out what we want the function to be, like add 2 numbers together, we can learn how to put together logic gates that implement that function. You've seen that before. You've built adders and things, but maybe you haven't thought about it that way. But we're going to go into more depth on this later, right? And this is a powerful thing too. And this is why logic gates are interesting and important, because if we can express it as truth table form, we can express it as a Boolean equation, and we can implement it as logic gates. Here's a logic implementation example. Here's a truth table. If you look at it for a minute, you can kind of get an idea of what this function is doing. It's a majority function. It's like a voting. It's voting on its inputs. If there's more than one, if there's 2 or more ones at the input, the output is a 1. If there's 2 or more zeros at the input, the output is a 0. Majority gate. There's several different ways to implement this with different combinations of logic gates. Here's one way to do it. It's not unique, interestingly. Truth table is unique. There's one unique definition for this function, right? But the logic implementation is not. So this gives us some freedom as designers to choose the implementation that suits our purposes. Maybe it's one's lower power, maybe it's faster, maybe it's cheaper than the other one. Right? So that's an important thing to know about logic gate implementations. My question is here, how do we know that these 2 representations are equivalent? So I'm asking you, you're doing your design, you think this will implement this. How would you check to make sure that they're equivalent? Yeah. Hey. Run it. Well, you mean simulate it.
Yeah.
Yeah, if you had a simulator, you could enter this into your simulator, and then simulator gives you a way to tickle the inputs and look at the outputs. You could simulate it.
Well, if there's like 2 to the 64 possible.
Well, no, this one, there's 3.
Okay.
There's only 3. There's 8 rows here. Look, you could do a, what do you call it in math? Exhaustive proof, or is that what you call it? Exhaustive proof. You basically try every combination. I could prove it by saying, if I apply 0, 0, 0, and just follow through. I put 0, 0 everywhere. The outputs of the AND gates are all zeros. All zeros into OR gate is a 0 here. Okay, and just tick them off one row at a time. Go through my truth table, check out apply the input combination and see what the output does. Right. That's what you could do with the help of a simulator if it's a complicated circuit. If it's a simple circuit like this, you can just do it by hand, right? Which is a good practice to get into. You can just kind of check yourself and check your work. All right. So we'll get back to this stuff later. All right. So that's combinational logic. We're going to talk when we get into it more later. We'll look at truth tables more. Look at networks of logic gates, and we'll look at how to go from one to the other and bring Boolean algebra into the mix at that time. The other type of block we need to understand are sequential logic blocks, not combinational, sequential. So here the output is a function of both the current input and the state of the state. So the state is a part of the circuit that is where the memory is. It represents the memory. So the state is a function of the previous inputs, right? So what we get at the output is not just a function of what's applied to the input. It's also something about the history, what's currently in the state value. And what's in the state value, it reflects what we've seen previously, right? So this gives us a way to produce or generate circuits that have much more complicated behaviors, right? They're context dependent or history dependent, right? Every digital system we design, we could represent this way, right? But usually break it into small pieces, and we use this concept in smaller pieces. Like, you know about finite state machines, this is a way to implement a finite state machine. This F here is just a combinational logic block, right? So if we know how to make the logic block and we have a way to store values and recall them, this is the memory. If we have a way to make memory, then we can make sequential circuits also. So let's talk about the state here, the state elements. So that's the other important component in our designs. In addition to combinational logic blocks is the state elements, because the state elements allow us to make sequential logic. And state elements are circuits that store information. For instance, registers or memories, right? This is a very typical one that we're going to use all semester. This is a register which has the ability to store n bits. Here's an input, and if you don't know this, I put that little dash through this line and an n there. So this is like a collection of wires, n wires all in parallel. Right? It's just a shorthand. So it has n wires going in to apply n bits, and it has n wires coming out where you can sense the output on these n wires. There is a special signal here which has this little chevron thing here on the symbol that tells us that the values are loaded into here and stored in here under the control of this load signal. Okay. Oftentimes it's a clock signal, and maybe it's a special control signal, load signal. And when that signal is asserted, values that are here move into here, and the output is replaced by those values. Right. So we have a way to control when we store. Right. So the stored values by the register appear at the output after some small delay. It takes a little time for the values to get locked in. Until the next load, the changes on the input are ignored. Right? So these get used for short-term storage, like in a register file. You can imagine implementing a computer and you need a place to store the registers that are part of the instruction set architecture. We also use these to help coordinate the movement of data around our system as we see. When we build pipelines, for instance, if you remember about pipelining. All right. So putting it all together, if we combine a bunch of combinational logic blocks and registers, then we have everything that we need in order to build a working digital system. In fact, every working digital system can be modeled this way. This gives rise to something we call register transfer level abstraction. Okay, we can describe the structure and the behavior of the circuit by a bunch of transfers. We move this value from this register to this value register, and in the process of it being moved, it moves through this combinational logic block and gets modified or gets combined with other signals. Right? That's all there is to it. That's the way to think about designing these systems. We're figuring out what's in the combinational logic block, figuring out where the registers are, and then controlling the flow of information through the system. And I'm introducing it now very quickly because we're going to go back and revisit this in great detail later. The other place where state elements come together is in larger memory. Sometimes we group together a bunch of registers, right? And use that for long-term storage, like cache memories, for instance. Right. Okay, and just to complete the story, this high-level introduction to logic design is you need to understand that there's a delay associated with the circuits that we build. Changes at the inputs do not instantaneously appear at the outputs. So here's an inverter. We'll look at this more in detail later. Here's the symbol for it. If I change the input, the output will change, but it will change after a little bit of a delay. If we didn't have that delay, we could build computers that work infinitely fast. Right? It just would defy the laws of physics. Right? As we'll see, when we change the output from one value to another, we're just moving charge. In the case of CMOS, we're moving charge from one place to another. Moving that charge takes finite time. Right? And it's primarily because there's finite conductance here. And there's some capacitance here. So it's a combination of the conductance, or its resistance, 1 over the conductance, and the capacitance that leads to logic delays, as we will see. It takes a finite amount of time to change the value, the voltage on a node, unfortunately. As designers, we'll learn what we can do to minimize that effect and make things go faster, right? But it's still always going to be there. The other thing is, as we put logic gates in series with one another, this is a really uninteresting case. It's just a bunch of inverters in a row. But normally you'd have AND gates and OR gates, or NANDs and NORs lined up. There's some propagation delay to get through those. It's roughly the sum of the propagation delays of the individual gates, as we will see later. So we have to deal with those delays. And if you look back at this diagram that I had before, and I said the essential thing we do on every clock cycle when we're running the system is we move a value from one register to another. How long it takes to move is determined by, let's say, how many logic gates we have in series in here and what the delay of a logic gate is. Right? This delay is going to dictate how fast we can clock the system. Right? The shorter the delay, the higher rate we could clock it. Right? So our job as designers is going to be to find that longest path, the path with the longest delay, and figure out how to make it go faster or make the delay be less or shorter. Oof. Any questions? Okay, just a little break. So if you're concurrent enrollment and you haven't talked to me yet, please do that as soon as possible so I can get you registered. I think everybody, did all the labs happen already, Tan? Did all the labs happen? Yeah. Okay, everything went okay. So if you haven't completed everything that's required for lab 1, make sure you complete it as soon as possible, certainly by the beginning of the next lab. Lab 2 will be more involved, we promise. So And then homework is going to go out, just to remind you, we have homework every week, problem sets. It'll go out Friday sometime, probably late afternoon, early evening. It was going to cover the concepts from last time and today, and then that'll be due in 10 days after that. Any questions about the class stuff I covered last time on the organization of class requirements, discussion labs? Okay. So we've got 15 more minutes. I'm going to try to talk about implementation alternatives and design flows. So let me just jump in so you see what I mean by implementation alternatives. Okay, so you're an engineer at a company. You need to build a product. Your product has some functionality. Let's say maybe you're making scooters, electric scooters, and you need some electronics in there to control the payment system or to control when to turn the wheels on or something about controlling the speed of the motor. There's some circuits in there that have to perform some function. Okay. So you're going to produce a bunch of scooters. You have to figure out how the control functionality is going to get implemented. Yeah. You have some choices. Okay, we're going to learn about those choices. You could do a full custom chip design. You could design a chip whose function is specially designed to do what you need for your scooter. Okay. In the case of full custom, what we call full custom is all the circuits, the transistor layouts are optimized for that particular application. Right. You could do another type of chip called a standard cell design, right? Typically called ASICs these days. Right? These ASICs are built, you have a library of predefined blocks, right, that are in some library, and you have tools that will put those blocks together for you. Those blocks are ands and ors and flip-flops and registers and stuff. Put those together and implement the chip for you, right, once you define what the logic design is. You have a thing called a structured ASIC, which I'll describe in more detail in a few minutes. But these are some prefabricated wafers with prefabricated transistors. And your job would be just to customize the connections between those transistors. Right. You have field programmable gate arrays, which have this funny name. They're not really gate arrays, but they act like gate arrays. These are arrays of logic gates or logic functionality that can be programmed by you without having to fabricate a chip. You buy an FPGA and then you can program the internals of it so it has a particular set of logic functions, implement some digital design. You could just get a microcontroller or a microprocessor and program it, write some code, right? It doesn't have to have an operating system in it even. It just run some program that executes the function that you need. Right? This might be a good alternative. Or if you have some special needs, you might have a domain-specific processor like a digital signal processor or a network processor or a graphics processing unit or a TPU, which is a tensor processing unit. Okay, so these are all your implementation alternatives. And which one you choose kind of depends on a bunch of factors that we will talk about. You can compare these by how flexible they are to change the design later. So if you choose to use a microprocessor and you discover that their specification for your scooter changed, right? The city of San Francisco says that no scooter shall go more than 15 miles per hour. You have to add functionality inside that's going to limit the speed. And your previous one let it go to 20. Well, you can just change the programming. You don't have to redesign the product and take advantage of that flexibility that's built in. On the other hand, if you had built a custom chip, like an ASIC or a full custom chip, and you wired right into the circuitry the fact that you never that the motor can go up to 20 miles per hour, oh, so you're in trouble then. You'd have to redesign the chip, right? So that's one way to distinguish these things, is how flexible they are. The other is, for a given functionality, what it will cost you, both in NRE costs, the non-recurring engineering costs, and in the recurring engineering costs, the part costs, right? And similarly, how much power that it'll consume and what the performance will be, right? So we have all the metrics that we had before, plus we have kind of flexibility as a metric. I'm going to skip this one now. And I'm going to just go to describing in more detail each one of these alternatives and what I think about them. So full custom. Here, circuit style and transistors are customized, sized, and drawn to optimize the die, size, power, and performance. Okay. This has because it's very labor intensive, every transistor is drawn and optimized for its particular place in the circuit. Right? It's very labor intensive, so the NRE, the non-recurring engineering costs, are high. It's also error prone, so you have to the engineers spend more time checking what they're doing than if the tools are doing more of the work for them. Right? But hand optimizing the layout could result in a very small die if that's important, which would mean a very high yield and low cost. So if you were making billions and billions of these things, it may be worth the effort to really optimize the die to get it as small as possible, because then the per die cost would be lower, even though you have a big NRE. Because the NRE, it gets amortized over a huge number, it almost disappears. I can tell you that nobody does this for digital chips anymore. This is common for analog design, except maybe some really special digital chips. Right. Also, you could optimize for extremely low power or extremely high performance. Right. So if you had some really special needs and you're willing to pay the cost, the extra NRE cost to do this, it might be worth doing it. But typically, full custom is really used for analog design, where the transistor layout and behavior is very important to the end result of the analog behavior of the chip. Right. So for RF front ends, for radios in our phones, and for D to A and A to D converters and that kind of stuff. All right, so I think I said this. So that's full custom. Standard cell, very popular, one of the most popular ways of building ASICs these days. This is built around a set of predefined and pre-verified cells. For example, and you'll see this if you take the ASIC lab, of course. You'll have a library of NANDs and NORs and flip-flops and maybe some bigger pieces like counter slices or buffers. Right. Here's a little picture of the layout ready for fabrication of a NAND gate. Right. But you'll have a library of these different things. Each cell comes complete with the layout, perhaps with different technology nodes. You might have the layout for 7 nanometer and for 13 nanometer, or it's kind of, layouts are specific to a particular factory these days. Then there'll be simulation, delay, and power models for each one, so that the simulator knows how to simulate it functionally and knows how to do a timing simulation. Right. I'll show you more of that in a few minutes. Chip layout is usually automatic, which is nice, and this reduces NRE. There's tools that will, if you can come up with a description of all the logic gates, all the cells, and how they're connected to one another, a tool will take those and line those cells up, because the cells are designed so that they can just line up next to one another and form a continuous power and ground connection. And then it will put all the wires to connect all the cells together in order to implement the circuit that you want. It'll do that in the computer file, and then you can send that file off for being manufactured. Right. So it'll generate the layout for you. So as a designer, you just need to specify the structure of the circuit. And these days, as we will see, you just write Verilog. There's tools that are going to take the Verilog and turn that into logic gates, or map your Verilog into a collection of cells from the cell library. So it reduces NRE, but it's a little less optimal than the full custom, right? Because there's only one or a couple of types of NAND gates in there, right? There's not that special NAND gate that's custom optimized for that particular place in your circuit. So there's compromises that are made. But it eliminates lots of errors and a lot of extra work. We talked about gate arrays. The gate arrays is an interesting idea. It's a little less popular these days. There's still some of this around, though. There's prefabricated wafers, and on the wafer are, for each die site, are just rows and rows of transistors. Right? And we know we can build any digital circuit out of transistors. Right? So what happens then is we can use some tools. We specify the logic circuit we want. And the tools figure out how to wire those transistors together in order to implement the circuit that we want. Right? And then the user, these prefabricated wafers are sitting somewhere on a shelf. And then when you as a customer say, I want to do my scooter controller, here's the circuit. I run it through the tools. The tools generate where the wires should all go. Then it goes to another factory, a different factory, that just puts those wires on the wafer. So a lot fewer processing steps are needed, and a lot less customization. So so it shifts a large portion of the design and masks. We didn't talk about masks, but a large part of the NRE is shifted to the vendor. Right? The user, or the consumer, the designer doesn't have to worry about the NRE associated with laying out the transistors. It's only the NRE associated with laying out the wiring. So it's shorter design and processing times. It's reduced time to market for the user. Okay. However, because of this highly structured layout, each cell, each type of gate is not optimized. So it leads to a larger area for subcircuits like flip-flops and even logic gates. Right? So it's even more of a compromise, but it's less NRE. Right? So the die is likely going to be bigger than a standard cell die, but you can get it quicker and you can get it for less NRE. And then things like memory is really bad, like cache memories and those kind of things, really bad in standard cells because the transistors are all really big. And a real cache memory, as we'll see, will make the transistor small and it's very dense. Right? So most of these structured ASIC or gate array processes will have some prefabricated memory blocks also, which can be used. Okay, so that's gate array. Field programmable gate arrays. This is the other very popular implementation technology that's used today, and it's what we use in our lab and in the other lab, in the FPGA lab. These are really interesting devices. As I said before, they're called programmable gate arrays. There's really no logic gates in here. What there are in here are rows and rows of combinational logic blocks. These are logic blocks that can implement any combinational logic function that we want, given a certain number of inputs. Right? So they're little programmable. Let's see if I have a picture of it here. Well, it uses a thing called a lookup table or a LUT. Right? One way to implement a logic function is just to store that function in a table. I showed you the truth table. You can think of the truth table as a little memory. I apply an input combination. It looks up that right row, the correct row of that truth table, and outputs the value that's stored in the table. That's the way a lookup table works. You know this from other classes that you can implement any mathematical function through a table. You just store all the values of that function in a table, and you look up that answer for a given input. It's the same idea here. This is another way to implement logic functions. So it's not really a logic gate, but it could do the equivalent of a collection of logic gates. So that's the way FPGAs are built. And the function that's in each logic block and the interconnection between the logic blocks is programmable by the user. So you send a bit stream into the FPGA and it configures it, programs it to perform some particular, it implements your logic, your digital design. So it's really nice in that you can change it. And the reason we like using it in the lab is that you make a mistake. It's not like if you design an ASIC and you had a bug in it, what do? You have to change the design, send it back for manufacturing, wait a couple more months, pay another $100,000 or whatever it is, and then test it. With FPGA, you can just reprogram it. And you keep reprogramming it until you get it right. So it's really nice for debug. It's nice for education because you can't, you can program it any way you want and you can keep reprogramming it. This is good for engineers and companies too because they need to worry a little less about getting their design exactly right because they could fix it later or fix it late in the design, in the product development cycle. All this flexibility, though, comes at a cost. A given function implemented in an FPGA is going to be bigger in area than a given function implemented in an ASIC. Right? It will also be slower because the wires are longer and there's more capacitance. And it's going to be more power because the wires are longer and there's more capacitance. So it's a less efficient in some ways, but it's a lot easier to design this way. You don't have to run through all these tools that do layout and everything. It's just, in practice, you write Verilog, you push it through the tools, and it programs the chip for you. So a chip that might take a year to design with a few engineers for ASIC, you could probably do in a month or so for an FPGA. Right? So it reduces the NREs. So that brings me to this diagram, I think. Oh, all right, let me just do this and then you can go. I let you go early last time. What this does is compare the total cost of designing a product with FPGA versus ASIC. Can you give me 2 minutes? Yes. Okay. All right. So I'll cover this more next time. But look, FPGAs, as I said, have low NREs, right? Because we don't have to produce the mask and go through all the detailed design process. But the die are bigger. So as we increase this shows as we increase the volume, what is the total cost to us as a company? We're producing these electronic scooters, right? If we need this number of scooter controllers, we're going to be at this point. If we need this number of scooter controllers, we're going to be up at that point, right? The slope of this is indicative of what the cost per die is, what we pay for each FPGA. The y-intercept is the NRE cost. Same thing for ASIC. ASIC has higher NRE, but per die cost is less, so it has a flatter slope, right? At some point, they cross over. So which implementation technology you choose depends on what your expected total volume would be. And that's where the marketing department comes in. They can tell you how many scooters they expect to sell in the lifetime of this product. Right? Okay. See you next time.